Okay, final instalment of Mr. Brown's revision, Year 12 Mechanics, Part 6. We're going to just talk about work, energy, power and efficiency. Okay, so we need to go through each of these. So work first of all. Basically, if you apply a force on an object and it moves, you have done work on that object. Okay, work is a measure of energy. It's measured in joules. Okay, so work is measured in joules because it's a measure of energy. Now, basically, you have to be careful though, because the force and the direction must be in the same. The distance must be in the same direction. Okay, so let's take this box. If I apply a 10 Newton force just horizontally, and it moves 10 meters in that direction, we could just simply use work equals force times distance, which is 10 times 10, which is 100 joules. However, as I said, we need to be careful. If the force and distance are in different directions, you need to work out and resolve the direction of the force, so you get the size of the force in the same directions as it moves. Probably easier to explain it with a diagram. So here's the box again. This time we apply the 10 newtons at 20 degrees. It still moves 10 meters horizontally, and you've got to work out the work done in moving it those 10 meters. So first of all, you need to work out the force in the direction of the movement. So because it's at 20 degrees to the horizontal, you've got both a horizontal component to that force and a vertical component to the force. We're interested in the horizontal. It's adjacent to the angle, so it's going to be 10 times cos of 20. Okay, this comes out at 9.4 newtons. Now you've got the force in the same direction, we use the work done equation. So it's work equals force times distance, which is 9.4 times 10, which is 94 joules. Fv is the vertical component of the force, and it's important that you realize this does no work on the box, as it hasn't moved in that direction. There is no movement in that direction, so it's done no work on the box. Now the only problem comes when you're considering work is if that force isn't always staying the same, it's constantly changing as the displacement changes. In this case, what you've got to do is you've got to consider a force displacement graph. Now, force displacement graph, what you've got is you've got the force in the y-axis and the displacement in the x-axis. You want the force in newtons and the displacement in meters. So if I just sketch a line there, the work done in this case would be the area under the graph. So what I would need to do is I need to split that graph up to as many sections as I can that make it as accurate as possible, and work out each individual section's area and then add them all together. Power now. Power, the definition is the rate at which the energy is being transferred, or the rate at which work is being done. So if you consider that definition, it's just going to be power equals energy divided by time, or I guess power equals the work done divided by time. Now just a useful equation comes from remembering work equals force times distance. So if I substitute that in, I get power equals force times distance over time. Distance divided by time is just velocity, so you get power equals force times velocity. Any of these equations can be used. Obviously it just depends on the question, what it gives you, what information, but P equals FV is a very useful one to know. Now power, remember, is measured in watts, where 1 watt is just 1 joule per second. Another section is efficiency. I'm not going to talk too much about efficiency. You'll have done this at year 9, year 11, all through your physics education. So efficiency is just the useful energy out divided by the total energy in. Or another useful one is the efficiency is the power useful out divided by the power total in. In which case, they're both useful, and if you want it as a percentage, just remember to multiply it by 100 at the end. Now, more often than not, a question comes up on energy changes, and in particular of an energy change of an object which is falling. So this is going to involve gravitational potential energy and kinetic energy. So consider a ball which drops through a height h to the ground. At the top, the ball has gravitational potential energy equal to mass times gravity times h. As it falls, all that happens is that gravitational potential energy falls into kinetic energy plus a bit of heat due to friction, but in most cases you assume that isn't applicable. So all the GPE turns into kinetic energy. Now you need the two equations. So GPE is mg change in height, and kinetic energy is a half mv squared. So if you know the height, you can find out the end velocity without having the mass of the object, because you're assuming air resistance is negligible. So the GPE, the potential energy at the start, just equals the kinetic energy at the end. So if you plug in the equations, mgh equals a half mv squared. Mass is on both sides, so they cancel out. So you get v squared equals 2gh, so v equals the square root of 2gh. So you can work it out without knowing the mass. Right, final past paper questions. Try this one. Question 4, June 2004. And question 3, January 2005. Obviously there are lots more questions out there. Please try as many as you can and see your teacher for any help that you need. Thank you. This is the end of the mechanics revision sessions. I hope you found it useful. Cheers.